operation.
So the objective of this experiment is to find out the coercivity and the recurritivity of a magnetic material. That is the objective. Mainly, what we mean by coercivity and recurritivity is that, suppose this is a magnetic material, we would like to magnetize this material. To magnetize this material, what we do is just put this in a magnetic field, and because of the presence of the magnetic field, it will get magnetized. How does it happen? This material is made up of molecules, and when the molecules are placed in a magnetic field, the molecules get aligned to the external magnetic field, and as per the alignment or the magnetic field, the polarity of this material when it gets magnetized is sustained. It is sustained for some time till the magnetic field is there, and while we switch off the magnetic field, that means when we demagnetize this material, what will happen? The dipoles that are oriented in a particular direction will get scattered again, will get disoriented again, and as a result, net magnetization will be zero, and the material again turns into a normal material, not a magnetized material. That is the basic idea, and we would like to quantify this activity. We would like to see how much is the input, how much is the magnetic field I have put in the input of the machine, if I call it machine, and what is the output, whether the objective is achieved or not. If achieved, at what cost? Ultimately, the cost is important. Why? Why we need to know that? Because I would like to use this material later on. How do I use it? How do I use a magnetic material? We would like to use this magnetic material in mainly, broadly speaking, in two ways. One is, if it becomes a good permanent magnet candidate, then I will be using it as a permanent magnet, all right? And if it proves to be a material, good material, to be a temporary magnet, right? When I switch it on, it becomes a magnet. When I switch it off, it becomes a normal material. So, to control anything, for example, the door, the window, the train, which is running in a levitation track, right? When I switch it on, the train should be going on. When I switch it off, the train should come down and get stopped. That is the idea. So, to quantify this process, what we need here, basically we need three apparatus, three main components. The first thing, to have a magnetic field, to produce a magnetic field, what I do, we take a solenoid. It's a coil basically wrapped in a circular way, and if I show it, this is like this. This is a hollow chamber. This is a cylindrical hollow chamber, which is made out of cast iron basically, and along the axis, when the current is passed through this coil, it becomes an electromagnet. Okay, this becomes an electromagnet, and along the axis, the polarity, the magnetic axis will be there. And if I place this material, the material which is to be magnetized, what I do? I put it in this, on this axis. That's it. All right. And where I have put it? This is the input. Okay. From this component, which is written as hysteresis loop tracer. All right. In this hysteresis loop tracer, what are the things available? You have a magnetic field, and this is going to the solenoid. All right. From the magnetic field controls this solenoid. Alright, so we have set it at B. We would like to see how much is the magnetic field. B is for magnetic field, and H is the magnetization. B is the input, H is the output. How much is the magnetization? Alright, so in your manual, it may be BH or JH. many a times you will find it JH. It doesn't matter the nomenclature. The basic idea is, if I say B is the magnetic field, then H is the magnetization. We would like to see that. So this is the input on this, for this coil, and to make it an electromagnet, I have put the material along the axis to be magnetized, right? And I would like to, this apparatus helps me, this component helps me to see three different attributes, right? One is B, another is B dot, that is the time variation. What is the rate of change of the magnetic field? And then what is the double rate of change of the magnetic field? That we would like to see. How do I do it? If you go through the manual, if you go through any textbook, you will see this is a consequence of electromagnetic impact, that is the induction that happens, and that induction depends on how much is the area through which either the input, that is the electric field, is varying. So finally, we would like to measure the flux. So the flux determines, suppose the electric flux determines how much will be the magnetization, right? And the reverse is also true. Magnetic flux determines how much is the electric energy I am achieving in a motor. In a motor, suppose what changes? The magnetic field changes, and magnetic energy, at the cost of magnetic energy, we are getting electrical energy. But here we are looking at the reverse side of that. So we are putting it in the input, we are letting in the electric field, electric energy, and because of that, the electric flux, how much is the change in the magnetic energy, that we are trying to look at. So this component, the right hand side component of this apparatus, is being used to magnetize this material. I am supposed to quantify this process, and that has been put along the axis of the solenoid. That's the left hand side of this component. If it can be focused, probably you can show it in a better way. Let me, for the time being, give an inclination towards the camera, and you can notice here there are certain things like phase, horizontal balance, and this is the input, and area ratio, demagnetization, DC balance, and then you have got Y, E, X, three terminals, and then these are the three things, B dot, B double dot, alright? This is the part we have said, and this also I have already told you about. This is the, when I am looking at this is 59 is the Gauss, this is in Gauss, here is the Z here, so 60, 59 Gauss, that is the magnetic field. If I look at this, this is the rate of change of the magnetic field. Here this is the, that gets changed there, B double dot, that is double time differentiation of the magnetic field. Okay, so another important thing is that, where do I look at? The magnetic field is being generated because of the electric field, and the electric energy is in the input, and the magnetic field is getting generated. That process is being visualized with the help of this electronic graph paper. This happens to be basically an electronic graph paper. This is as good as a graph paper like this, for example. This is a graph paper, right? Isn't it? And instead of this, the hard copy on a piece of paper, we have a graph paper in this, on this device, right? So this is electronic graph paper. As initial, along like this, we have an x-axis, we have a y-axis, right? So we can plot whatever is getting plotted on a piece of paper, that is getting plotted on this component of this apparatus. We call it cathode ray oscilloscope, or CRO. Very, very versatile device. Anyone who would like to work work with the electric and magnetic gadgets, you have to have a good hand with this. You have to know all the facilities, all the attributes of this machine. I am saying machine, right? So this is basically, as I have said, digital graph paper. So the functioning is just like a old television set you have in your home. if you have one. The old television set, sometime later maybe on a different video we'll discuss about the construction of this machine. Very interesting, particularly those who are interested in instrumentation and electronics. This is very, very interesting how this is the cathode ray oscilloscope works. The basic principle is getting used is Lorentz force, right? We are using in perpendicular direction, we are using the electric field, then the current is there, and accordingly there is some displacement of the electron. And when the electron gets displaced, if the displaced electron is allowed to interact with some fluorescent gas, then you get the impression of on this display, right? That is the basic idea. So we are not going into details of this construction of this, the inner side of this instrument, but we are interested in the in applying this gadget for helping us to document, to record the output of this experiment we are setting up, right? So what we are doing is there are two channels, channel 1, channel 2. Channel 1, if we are saying Y, channel 2 is X, and we are giving this both in the input as an this input is coming as an output of this device, right? You can see here X, Y, and this is the common. Common means the ground. So from both these channels, the common one is inserted in this common here. This is ground, and X and Y we are putting in just like X-axis and Y-axis. That's it. For the time being, it is just like that, and you can see here 0.5 volt, this is 2 volt, right? Channel 1, 0.5 volt, channel 2, 2 volt. What does it mean? Channel 1, that is the x-axis. Along the x-axis, suppose I say that this division is 0.5 volt. One division is 0.5 volt, all right? And along the y-axis, one division is 2 volt. When I change this Y, okay, you can see that this is getting changed, right? This is getting changed. So we would like to set it at, suppose 1 volt and 1 volt. So 1 volt and 1 volt. What does it mean? One house, the distance of one house along the x-axis is 1 volt. The distance of one house along the y-axis is also 1 volt. That's the unit is voltage. Because ultimately, if you go through this manual or any textbook for that matter, finally the magnetic field and the magnetization, the input and the output, can be calculated, can be determined with the help of the variations of magnetic field and time rate of change of the magnetic field and the double time differentiation of the magnetic field. If you solve that differential equation, ultimately you can come up with B and H, and B and H comes out to be this distance and this distance. If you measure this distance and this distance, and you know certain calibrated information of this setup and this sample you are using. See? You can see there is no loop because I have taken out the sample. So if I put it, you can see the sample. This is the first, this is kind of a tip for any experiment you do in the laboratory, for that matter. So whether whatever is in the output is actually coming from my setup, my experiment or not, how can you check? How can you check? The best way is just take it out. You see nothing is there. When you insert it again, you get that what was claimed by you that this is the output, desired output. So that gets proved, right? So this is the output we are looking for. What it tells me, without going into details, if I tell you that along the x-axis, it is telling me along the x-axis is the input, that is the magnetic field I am putting in, I am inserting in, and the magnetic field is 59 Gauss. The 59 Gauss magnetic field is getting applied to whom? To this magnetic material, right? Which is to be magnetized. Right? So, and as a result, it is getting magnetized. That is my claim. Yes, I can see that it is getting magnetized up to this, from this point to this point along the x-axis. Right? I can see that there was no magnetization showing up. I am putting something, I am giving something in, but there was no output. But all of a sudden, at this point, this is rising up. That means the material got magnetized after some initial hiccups. Initially, you are supplying in magnetic field because that energy was used to get the dipoles aligned along a particular direction. Because the dipoles inside that material was disorganized, disoriented, right? Randomly oriented, so that net magnetization was zero that time. Okay? Because sum of forces, there are vector quantities, will be zero ultimately. Magnetic field is a vector quantity. Sum of forces, vector relation we are talking about, right? So when you are supplying in some energy initially, that energy is getting used up to align these molecules, dipoles, right, along the given direction of the field. So that is showing up here. After that, it shows up. That means after that, he is magnet. This material is magnet because initially you have supplied some energy and it is getting magnetized. Now you just increase the magnetic field. You can see that there is some increment in the magnetization average. This is 96 Gauss. You go more, you can see higher up. It is rising up. The loop area is also getting enlarged. You go higher up, again, this is also rising up, and the loop area is also going up. Now 227. Right? There is incremental changes, but still there are changes. I am at 350. So up to 350 around you can go for nickel. The sample we are using here is commercial nickel. You can use other magnetic material as well. For the time being, we are using commercial nickel. Nickel means mostly in steel and nickel, that is the most preferred material we use for making it commercially viable. Anything which is to be magnetized, right? So, that way, this material is getting used. Now, what I was telling you is, suppose I want to come down. Take it here, 97 Gauss. At 97 Gauss, I see that this is showing up. Qualitatively at least, this is showing up that there is magnetization. Not non-zero magnetization. Magnetization has happened. What after that? Why it is coming back? Because even if when I am taking out the magnetic field, I am reducing, I was increasing magnetic field, now I am decreasing magnetic field, right? Even if I am decreasing magnetic field, I am making it as small as like 27 Gauss, even that I can see there is some non-zero output. Ideally, when the input is zero, the output should be what? Zero. Simple logic, right? This material was not a magnet. This was capable of getting magnetized, but he was not magnet. But see, on this graph paper, at this point, the center point, when x-axis value is 0, x-axis value is 0 means magnetic field is 0, magnetic field is 0. Output should have been 0. You should have a dot, but no, you are not getting a dot, you are getting still, you are getting some non-zero magnetization. What does it mean? It means that there is some retention of the magnetization. The magnetic dipoles, the magnetized dipoles, while they were demagnetized when the magnetic field applied was taken out, right? Even then, because of the inertia, the dipole wanted to remain along the direction of the applied field. They remain in that position and they retain the magnetic impact on them. So we have seen both these phenomena. These are very, very important phenomena. One is called coercive. The material was coercive. Higher this horizontal width, greater will be the coercivity of the material. Coerciveness means it is energy is getting in wearing and tearing up the material. That's it. No productive work otherwise, right? Productivity is lesser when the coercivity is higher. Productivity is lesser. That energy which is supplied in is getting used up. I am not saying wasted. I am saying used up in wearing and tearing, aligning and disaligning the molecules. All right. So that distance from this distance to this distance is called coercivity. Twice the loop width of this loop. This is a loop. Right? That is called coercivity. And from this to this point to this point is known as retentivity. Because why retentivity? Because the magnetized material has retained the magnetic impact, right? Magnetic property, magnetic behavior. So from this point to this point, we call it retentivity. From this point to this point, along the horizon, we call it coercivity. You will find these terms here also. And we know when some material, in case of some material, suppose in case of a particular material, the retentivity is very high, coercivity is very less. Right? So coercivity is less, retentivity is very high. Suppose I want to write it here. If you have a, just can you pass me a paper? So suppose you have something like horizontal. First saying, suppose you have a loop like this, right? So this is a loop. When this area, this height is higher and this width is lesser, we call retentivity is very high, coercivity is very less. And we decide that this is going to be a good candidate to be a temporary magnet. When I switch it on, it goes up, it shows up magnetized behavior. That I am getting magnetized, you use me. When I switch it off, it comes down. So ideally, suppose if I have something like suppose it shows up like this. This is the best electromagnet I am going to use. Best electromagnet. Suppose I have another material where it is like this. Out of these two materials, there are two materials. For one material, I have got the loop like this. Another material, I have got the loop like this. I would be preferring this material over this material to use it as an electromagnet. Because for electromagnet, I need switch on, switch off, right? So retentivity. Why the coercivity? That means this is more coercive than this. So easily it will go up, that is, it will show that it is magnetized, right? At a lesser time, lesser energy in the input, you will show magnetized characteristics, and then when the magnetic field is taken out, you will be dying down. That's it. That is the requirement. But again, suppose in some material, suppose you have two materials like this. These two materials. One is this, another one is this. Right? What you see here, what is varying here? Mostly the retentivity part, isn't it? This is higher retentivity here, this is lesser retentivity here. So I would be preferring this material over this material if I need a permanent magnet. Right? The magnet, the requirement of the client is to have a permanent magnet. All right. So I will go for retentivity. Higher retentivity means better candidate to be a permanent magnet. So I will pick this. All right. So that's it. So suppose ideally, what does it mean? That means this area. Suppose in some cases the loop is like this. the loop is as small as like this. Right? In comparison to this and this material, here I can see the loop is very small. Here the loop is very high. What does it mean? This is a good candidate to be a switch, kind of a switch, magnetic switch, for example. Right? Suppose the door needs to be open and closed, right? And that should be controllable also. It cannot go wrong, right? Just like a metro in Delhi metro, they switch on and switch off. Suppose you need a material to control it. So you will be picking up this material rather than this material, right? So what we understand is, lesser this loop area, better is its application in terms of a switching device. Okay? So in the practical way, if you look at this area, tells me how much is the loss. Higher this area, higher is the loss. The reverse logic of this. Lesser this area, lesser is the loss. Lesser the loss, higher is the application in terms of a switch. In a switch, the loss should be minimal. The time loss, the energy loss should be minimal. Right? So this is a good switching device. But suppose in some cases loss is very high. A transformer, very high loss. Right? So this is known in case of a when if this is happening here also. We call it hysteresis loss. Right? If you do some little bit of electromagnetic theory, you will be doing it in theory. So this tells me this is along this, suppose this is B, this is H, this is B, this is H. So this area under the curve, right? Area under the curve on this actually gives me B cross H. These are the two vector quantities. This area under the curve gives me pointing vector, the magnitude of the pointing vector. And the pointing vector is the energy, electromagnetic energy. So this is telling me area under the curve, that means this area tells me the loss. How much is my loss? In the process of getting it magnetized, how much is my loss? So this is the background, this is the physics of it. Follow me. So we know now what is this, how to use it as an output. We have to trace this first. Suppose just like this, we need to take a picture or a tracing. So we have to trace it using a tracing paper, or finally, what is the use? Why we would like to trace it? Because we would like to calculate, we would like to figure out three things from here: the loop width from here to here, then the y-axis, that is the retentivity part from this to this, and from tip to tip. That means this distance. This is the one tip, and this is the another tip. So this much is the duration. This much is also to be figured out. From this to this, tip to tip, and the y-axis intercept, x-axis intercept. This is x-axis intercept, this is y-axis intercept, right? All these three quantities, along with on this device, for nickel, the manufacturer tells us that this to calibrate it for nickel, so that this gives me right estimate. He tells me that the area ratio of what? Area ratio of the sample to the coil, this coil. The sample and to this coil, area ratio should be around 0.133, and the demagnetization factor, this is a factor. We will go in details while in the theory class, but this demagnetization factor should be close to 0. This is 0.0029 or something. So we have set it in that, and if you put it in the relationship, which is given in the tail deriving these equations, ultimately in the expression of B is equal to and H is equal to, these are the two factors you need to know. Area ratio. Area ratio of what? The sample to coil area ratio. That is set at 0.133, And the demagnetization factor is also set at close to 0, that is 0.0029 or something. That has been set, and it should be noted down by you, right? While taking the readings, the first observation is this: how much would be the demagnetization factor, how much would be the area ratio, that you need to note down. And other things that like the phase, horizontal balance, DC balance are all set. So we are not needed, right, to alter these things and to modify these things. Only what you are supposed to do is just keep varying this magnetic field, and then keep measuring these three things: x-intercept, y-intercept, and tip-to-tip. Because you can see here, just look at that, when I change this magnetic field, right? Magnetic field, that is getting changed. Magnetic field, that is getting changed. So this should be recorded in your table. The tables are given here, right? And finally those should be plotted. Whatever is getting recorded is getting plotted, right? So these are the observations tables, the observation tables. Right? So basic attributes to be noted down are these factors, and from these input parameters and the output estimates or measurements, ultimately we can find out, we can figure out the coefficients, required coefficients, and then the retentivity and the coercivity of the material being used. So you use the second material, this is the first material. Now you use the second material, go by the same logic, same procedure, follow the same procedure. You have two sets of graphs and the readings and the numerical values, compare and tell me which one is good as a permanent magnet, which one is good as a temporary magnet, electromagnet. That's it. That is the objective, and that is how we achieve this objective. Okay? But be careful about certain things while tracing this, because you cannot trace it here. You cannot use your pen and do it here, right? Be very careful, because this or the pencil will make marks, and which is not good, because you cannot modify, you cannot rub it off if something is stuck on. So instead, what you are supposed to do, you have to take a trace paper, ideally the graph paper only. The graph paper, use some oil that is available, glycerin, and then use it as a tracing paper, put it here, then plot it, trace it. Plot means trace it properly using a pen or a paper, and then note down this. That is 1 volt, 1 volt. X-axis 1 volt, 1 axis volt. These are the scales, right? At this scale, this is your reading, and accordingly, then using that, put on this your table, down, note down. How much is the y-intercept? How much is the x-intercept? How much is the tip-to-tip? That is how you are supposed to do. And another important point is, while using this solenoid, right, be careful that there is no other interfering devices around. Suppose there is an electromagnet, there is another coil nearby. That should not be there, because that will be an interference. You want to make sure that this magnetic field is the only magnetic field that is getting applied on it. Arc magnetic is there, that is uniform, right? That doesn't matter. That is very feeble also in comparison to this magnetic field. We are not much worried about that. Apart from the arc magnetic field, the horizontal component of arc magnetic field at Gauhati, we are sitting at Gauhati. So there should not be any other interference. This magnetic field, 96 cos, is the magnetic field getting applied on the material. That's it. So if there are other gadgets, either that should be taken away or it should be switched off. Okay, thank you.